an example which are not really frequently traded options, but it's a good example to kind of make an exercise, practice all we have done so far in the continuous time part of the course. So what is it we have done? We use Zito's rule, we change probabilities. Okay, I'm not going to do differential equations here. I'm just going to do risk neutral pricing in continuous time here. And there is going to be one new thing, which is going to be we will have two Brownian motions instead of just one Brownian motion. Because in addition to having a foreign currency, I'm going to introduce a domestic stock, or let's say a domestic equity index. And so this is one of the so-called Quanto options. In particular, it's called a Quanto forward. It's an option which pays the difference between the domestic index at time capital T minus a constant forward price. However, it pays whatever that difference is in the units of foreign currency. It's a bit strange type of thing. You look at an American index or American stock, whatever, and let's say it's $900 and minus F, let's say F is 100, so that's $800. It would actually pay 800 euros. Okay? So you just look at the value of the American index in dollars minus F, and then you get, if you hold this option, you actually get that number in euros, in foreign currency. Okay? Again, not maybe something that is traded very often, but useful for practice. So what am I going to do? How am I going to price this? In principle, I could write differential equations, but I'm going to use it with risk neutral pricing. I have to compute. So my payoff in dollars is going to be this difference times the exchange rate, right? Because I get this many foreign currency units, so I have to multiply by the exchange rate. So I want to price this, which means I want expected value of this difference times R of capital T. I want it under the pricing probability Q. So I will need dynamics of R, and I need dynamics of S times R, okay, for that. So I go back to the previous slide where that is computed. We already know for the exchange rate, we already know how, from what we just did, we already know how WQ looks like. It looks like this. I'm going to then I replace dW by dWQ using the formula I wrote in red in the previous slide. Right? I replace dW with dWQ. If you do that, you can easily see that this never changes. Instead of the drift mu r, it's going to be replaced by r, but not only by r, it gets replaced by r minus rf. Again, this is the same as with the dividends. In the stock dynamics, we had r minus small q. Here it's r minus rf. Again, that's just by replacing in dr, in the model for dr, which was mu r dt plus sigma r dw. You replace dw by dwq from this relationship, and you will get this. Yeah. Okay, when you do that, okay, maybe just to write it here down to remind you in case you forgot that. So I know that dr is equal to r mu r dt plus sigma r dw. And I also know from here that dw is dwq, and now I'm going to try to write it without those typos. So minus mu r, not mu q, minus r minus rf over sigma r dt, right? So this is what you replace inside the second red line for dw. Then you're going to get this dr under the q probability. Okay, that's what we are doing. We want to write everything under the q probability. So again, replacing this dw here by this, we get this. Fine. And I need a model for the domestic index. And I'm going to write the model right away under some Q probability, under which I'm going to assume no dividends for the index, just to keep it simple. So I know if there are no dividends, under Q, the index has to pay R in terms of expected return. And I'm just going to call this Brownian motion ZQ. Okay, and maybe I want some correlation between the index and the exchange rate. And I'm going to assume that ZQ, BMP means Brownian motion process. That I'm going to assume that ZQ is a Brownian motion process which has instantaneous correlation ρ with WQ. Just to remind you what we mean by this correlation, we mean that E Z Q of t times WQ of t under Q probability is rho t. And that's what we mean, that's the definition of correlation. This is consistent with the Black-Scholes-Merton model in which all parameters are constant. In general, a correlation could be time dependent, so you could have, in fact, in general, that this is EQ of some integral 0 to t over rs ds, so it could be time dependent ρ and even random. But that's not what we are going to assume. We are assuming constant correlation like that. Okay, then I have to do Ito's rule on the product. Remember, on the next slide, I told you I was going to need a product. So I look at the Ito's rule on the product as times R under Q. And so it's the usual product, which is SDR plus RDS. But then there is going to be an extra term because there is correlation. So what is the extra term? Well, you have to go back to look at the Ito's rule for the product, but I will just tell you here what it is. So the extra term is you multiply dW terms, which is R, sigma R, S, sigma S, and you multiply all of that also by rho. Okay? So you have R, sigma R, S, sigma S, and times rho. So that's this times dt. That's this this extra term, rho sigma R sigma S or rho S. Other terms come from the usual derivation of the product, SDR plus RDS. And this is the extra Ito term. Okay? So you do Ito's rule on the product and you get this. Okay? Again, if that was too fast, you can just go back to the slide with the Ito's rule for the product and make sure that you know how to get this from that rule. Fine. Now I am close to being ready to compute everything. So I have my Q dynamics for R and I have my Q dynamics for S times R. And then I go to price this payoff. Okay, it's in dollars. The value is going to be discount in dollars. It's going to be discounted expectation under Q of that payoff. I split it into two parts, two expectations. And what do I want? I want the formula for F. I want to find F such that this is 0. As usual for forward contracts, I want the initial price to be 0. So if I put this is equal to 0 and solve for F, F has to be equal to the ratio of expectation under Q of S times R over expectation under Q of R. Okay. It has to be that's what F has to be equal to. So now it's just a question of computing these expectations. And I have some formulas here, but let me give you a general method for computing these type of expectations. You can do this in different ways. You can use a normal distribution moment generating function, but here is a different way using this simple ordinary differential equation. So look at the following. Look at any process dx which satisfies ax dt plus something dw plus something dz, where w and z are Brownian motions. In fact, it's not so important that this is bx and this is cx. It's just important that this is a dw term and this is a dz term. Okay? And I want to compute the expected value of x at some time t. Okay? I claim this is simply x of 0 times exponential of this a here, which is assumed to be constant, a times t. Okay? So whenever I have a process like this, which has constant a times the process itself, dt, plus Brownian motion martingale terms, then the expected value is just x of 0 exponential of that constant time t. That's the general rule for these expectations. Okay, so one way to see that, so there's a one-line proof here. If you know ordinary differential equations, one way to see that is if I take expectation here. Okay, really I will have to write this in the integrated form and then take expectations. But I'm just going to formally take expectations here. It's going to be clear what's going on. So if I take expectations, I have a d of the expectation. These two will disappear because they will have expectation 0. This is because these are stochastic integrals and therefore martingales. So they will have expectation 0. They will disappear, and I will only have a times expectation of x of t dt. Okay. But what is this? Well, I can write this as a ordinary differential equation. You know, just in the usual form, it would be divided by dt. I can write this as d dt of e of x of t equal to a e of x of t dt. No dt anymore. So, you know, just think of e of x of t as some function f of t. So this just says that f prime of t is equal to a times f of t. But that's the simplest possible ordinary differential equation for which we know that the solution is in fact exponential of at. And then you have to account for the initial condition. Initial condition is that 0 has to be x of 0, so that's why you have this x of 0 here. Okay, so the function a expectation of x of t satisfies this differential equation with initial condition x of 0, and the unique solution of this simple linear ordinary differential equation is this function. Unique up if you know the initial condition. Okay, so we have a general formula for computing expected value of processes like that, but that's actually exactly what I need, because my dr is a process like that. It's r times a constant dt, and my sr is a process like that. It's sr times a constant dt. So I know how to compute expectations. Expectation of r is r0 e to the constant times capital T. The constant was r minus rf if you look at the previous slide. And here it's s of 0 r of 0 e to the constant, and this was the constant times capital T. Okay, so that's just using the general formula on these two processes, which are both of that type that I have in the next slide as dx. And then I just divide these two, right, to get my forward price. R of 0 will cancel, minus rf will cancel, one of the r's will cancel, and I will get this formula. Simple formula for the forward price of a Quanto forward. It's s of 0 times e to the r plus sigma s sigma r times rho. What is this, statistically speaking? This is actually the covariance between s and r, between the index and the exchange rate. Because you have correlation times the volatilities, times the standard deviations, if you want. Correlation times the standard deviations is the covariance. It's the covariance of the log, actually, of the log returns of the s and r. Okay, so it has the interpretation of covariance. So it's a simple formula, almost as simple as when R is 0, which was the case with a regular forward contract, right? With a regular forward contract, we didn't have this term, this was 0. But for the regular forward contract, we were able to get this formula by simple no arbitrage arguments without any model, any mathematics. Here we can do that, and in fact, it wouldn't be easy to get this formula just by intuition or by some kind of no arbitrage argument, because it does depend on the mathematical model. We do assume that we have constant correlation, we do assume that we have constant volatilities, we assume Black-Scholes Merton model here, and that's why we cannot really get this by no arbitrage, because it's not true for any model, it's true for this specific model. And it would be hard, even if it's a simple formula, it would be hard to get it just by kind of intuition. We kind of have to go through this mathematics. It's not hard once you know this martingale pricing and this one formula for computing expected values and Ito's rule, right? These are the things we've used. It's not hard, you get it. And this is the power of the martingale risk-neutral pricing. If the solution, if the price is simple, then it's a fast way to computing it is using risk-neutral pricing. Okay. If it's not simple, or if it cannot be found, then you have to do numerics, and you can compute these expectations numerically if you want. But if there is a simple solution like here, then you can find it pretty efficiently using a risk-neutral pricing. Okay. So that's the point of this example. It shows the power of risk-neutral pricing for a simple contract. Okay. So that's actually it for this set of slides.